In this video, we'll start with a proof of Theorem 4 that we briefly discussed in the previous video. So Theorem 4 is right here. So in order to prove this, we're going to start off with letting phi of x be a solution to the non-homogeneous differential equation in 27, or named 27. So basically what we want to show is that this consists of a particular solution plus the solution to the homogeneous equation. Now, we know that yp of x is a solution to this non-homogeneous differential equation. So I'm going to rewrite that in operator notation. L of y equals g of x. And so what we need to know here is that L of y is equal to the linear differential operator, the nth derivative of y plus p1 times the n minus first derivative of y, and then plus dot 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 plus pn times y of x. And here p1 and pn are also functions of x. So this is just a shorthand notation to rewrite that equation 27. Okay, so now let's take a look at what we know when we apply the differential operator to the difference of phi of x and the particular solution. So we know that the linear differential operator acting on these two functions is linear. So we can write the linear operator on phi of x minus the linear operator of yp of x. Now, since both are solutions to the non-homogeneous differential equation, we know that both of these functions, or both of these linear differential operator acting on the function produce g of x. And so that is 0. So the linear differential operator acting on this function produces 0. So in other words, phi of x minus yp of x is a solution to the homogeneous differential equation, right? So when we plug that in for y, we get 0. So that means that phi of x minus yp of x is c1 times y1 of x plus c2 times y2 of x plus dot 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 plus cn times yn of x. And now we can bring the particular solution to the other side. So we have that phi of x equals the particular solution of x plus c1 times y1 of x plus c2 y2 of x plus dot 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 plus cn times yn of x. So this is yh of x, the solution to the homogeneous equation, plus a particular solution gives us the general solution. So that's what we needed to show. So as long as we have a fundamental solution set for the homogeneous equation and a particular solution to the non-homogeneous equation, we can combine those two to find all solutions. Now let's end this video with an example where we can apply this finding. So we're looking at a differential operator L defined by d cubed minus 2d squared minus d plus 2 acting on y. We want to find a general solution to the differential equation L acting on y equals 2x squared minus 2x minus 4 minus 24e to the power negative 2x. And we're given that a particular solution, yp1 of x equals x squared, is a solution to the differential equation L acting on y equals 2x squared minus 2x minus 4, and yp2 of x equals e to the power negative 2x is a solution to L acting on y equals negative 12 e to the power negative 2x. Furthermore, we're given that y1 of x equals e to the power negative x, y2 of x equals e to the power x, and y3 of x equals e to the power 2x are all solutions to the homogeneous differential equation. Okay, so first of all, in order to find a general solution, we need to find a particular solution, and we have parts here. So one way, or one thing that we can see is that yp1 equals x squared is a solution to the differential equation where the right-hand side is equal to 2x squared minus 2x minus 4, and that's exactly what we have here. Now, on the other hand, we know that a particular solution, yp2, solves the non-homogeneous differential equation L of y equals negative 12 e to the power negative 2x. Now, when we compare that with the minus 24e to the power negative 2x, we see that the right-hand side here is twice what we're given here. So when we want to use that second particular solution, we need to multiply that by 2. So here we multiply that by 2. So our particular solution is given by the linear combination of those two. So it's x squared and then plus 2e to the power negative 2x. So those two together take care of that non-homogeneous part. So now we want to take a look at the homogeneous part. YH of x equals C1 times Y1 of x plus C2 times Y2 of x plus C3 times Y3 of x. And that gives us C1 e to the power negative x plus C2 e to the power x plus C3 e to the power 2x. And then finally, we have that the general solution y of x equals yp of x plus yh of x, and that is given by x squared plus 2e to the power negative 2x plus c1 e to the power negative x plus c2 e to the power x plus c3 e to the power 2x. And so that is our answer to this differential equation. So that's the most general solution to that differential equation. Now, something to note, and this is what we'll see later on. I'll write that here in other videos, but note that when we have the differential equation d cubed minus 2d squared minus d plus 2 acting on y, and that equals g of x, that another way of writing that is y triple prime minus 2y double prime minus y prime plus 2y equals g of x. And when we look at this equation and we want to know what the auxiliary equation is, we see the following. That's r cubed minus 2r squared minus r plus 2 equals 0. So what you should note there is that if we have the differential operator form, we basically get the auxiliary equation for free, right? The d cubed becomes an r cubed, the d squared becomes an r squared, the d becomes an r, and then the constant stays a constant. So keep that in mind for the next few videos in this chapter.